Okay. All right, so how do we actually come up with a solution for temperature using an analytical approach? We're going to follow the same steps we've been doing. It mirrors a lot what we've already done, but there's some slight differences that then lead to a bit more complexity in this solution. All right, so first let's start off by drawing our differential control volume. So here we've got our fin. We're going to draw our differential control volume. Coming in, we have, let's see, this is now the x coordinate, right? So q dot in the at x. Leaving the control volume, we have q dot at x plus dx, right? So this thing must be dx wide. Okay, but now we have heat leaving this control volume, right? We have heat leaving due to convection. So we'll call this q dot convection. All right, how is this any different from the generation case, by the way? In generation, we would say, here's my g dot triple prime, or here's g dot triple prime as a function of position. And we would just plug that in. And now we would have an equation that had a constant g dot, or it would have a function of position only, right? Now q dot convection is actually depending on the temperature. It is not just a function of position. It depends on the temperature itself at that location. So q dot, all those q dots are now temperature dependent. Okay. So let's see. Let's do the energy balance here. We'd say q dot x is equal to what's leaving q dot convection plus q dot x plus dx. Okay, we're gonna expand this guy out, right? This is q dot x plus dq dot x dx. Dx, right? Same thing we did before. So then our equation becomes q dot x equals q dot convection plus just making that substitution. Q dot x plus dq dot x dx. Dx, the q dot x's go away. Okay, and we're left with d q dot x dx times dx equals, bring the minus, so it's minus q dot convection. All right. Again, stop and think about what we're saying here. We're saying the rate of change of heat transfer as a function of position x is no longer zero, right? It's something. It's related to the loss due to convection. Okay, so you're getting a different q dot x than you are q dot x plus dx. And that should make sense, right? We're losing heat from the control volume. Again, we are talking about temperature distribution only in x because we've now made the assumption. We've made the assumption that the BO number is much less than zero, or much less than one. I'm sorry, it's really close to zero. So this is approximated by a 1D solution. So we're still losing heat in the y direction. That's still true, but the solution is only going to be a function of x. Okay. All right, so let's continue on this. So now we need rate equations. So we need a rate equation for q dot x. This is a conduction problem, so we should bring out Fourier's law. So this is going to be minus k AC times dt dx. Okay, we need a rate equation for this guy, right? And this is now q dot convection is now what? My h bar times the area. Well, what's the area for convection, right? Look here. So this and this. And if you had it in like 3D, right, it might look something like this, right? So we'd be taking the perimeter of that fin times the width, which is dx. So this is now h times perimeter of the fin times dx times T minus T infinity. Right? T is the temperature at that whatever position x. Okay. Don't get confused, right? Perimeter times dx, we're talking about a control volume, not the overall fin itself, right? This is just an analysis on this differential control volume. Okay, so carrying on, now let's make our substitutions back in. So we have d dx of, we'll substitute Fourier's law, minus k AC dt dx. Times dx, don't forget that, is equal to minus perimeter times dx times h bar times t minus t infinity. Okay, now look what we can do. We have, over here we have dx, over here we have dx, and those can cancel out. Sorry, I wrote under my thing. Right? You always should get to a point where you can cancel out the dx's. If you didn't cancel out a dx, you probably made a mistake. Okay. All right, so let's see, simplifying this out, remember we want to divide off all the constants so that the highest order term sort of stands by itself. Okay, so if we do that, we have d dx of dt dx. You could also write that as d squared t dx squared is equal to, bring everything over, I have perimeter times h bar over k ac times t minus t infinity. All right, so now we have this equation. It kind of looks like what we had before. We have this differential. Before, what we would do is we bring the x stuff to the right-hand side, the t stuff to the left-hand side, we'd integrate and we'd solve. All right, in this problem now, you can't do that. And why? I mean, you could try to do it, right? We could try bringing the dx over here and integrate. But if we do that and do this integral, the problem is we have t over here. Right? T still appears, and there's no way to there's kind of no way to deal with that directly. So we could try that. We'd run into a problem. We don't know what t is yet, so we can't integrate that without knowing what t is. We're trying to get to a function of t. We don't know what it is, so we can't integrate that as we could before. Okay, so instead of doing that, we'll get rid of that stuff. So instead of doing that, we're going to need to kind of try to bring all the temperature stuff to one side, and then we'll see how to proceed. So let's bring all the temperature stuff over here to the left, d dx, dt, dx, c minus perimeter, h bar over k ac times t is equal to what's left on the right-hand side, which is perimeter, h bar over k ac times t infinity. Okay, remember, t infinity is a constant here. Okay, so now we have this stuff on the left and stuff on the right. What's on the right is a constant. Right? Keep in mind that's a constant. You might go through this solution and maybe you have convection that's, maybe temperature is a function of position on the external side, and it might not be a constant on the right-hand side. But what you should end up with is all the temperature stuff on one side, and then everything else, which may be a function of x, on the right-hand side. Okay, so you probably have seen equations like this before. Probably either in a math class or previous heat transfer class. You may or may not remember how to solve them. Okay, so what we need to do for this is break this into a particular and a homogeneous solution. So we're going to say this solution T that we're trying to find has to be the sum of what's called a homogeneous solution and what's called a particular solution. So we're going to make this substitution to say that we're going to add these two solutions together in the end, and it's going to give us back our full temperature solution. Okay, so if we do that, let's see. So if we do that, we're just basically taking this and substituting it anywhere we see temperature. Oops, temperature's not over there. Right, anywhere we see temperature, we're going to make this substitution. You might be thinking, why are we doing this? How is this going to help? Well, you'll see in a second. Okay, so hang with me. So, okay, let's make the substitution d squared. First, let's do th. Okay, d squared th over dx squared minus perimeter h bar over k ac times th. Let's see, and then we're going to substitute in TP. Right? So we've done our TP, so it's the same thing, d squared plus d squared TP over dx squared minus perimeter h bar over k ac times TP. Okay, and then all of that has to equal the right-hand side, which remains unchanged, which is minus perimeter times h bar over k ac times t infinity. Okay, so that's now our substituted equation. We've made the substitution in hopes that we can actually separately find the solution for a homogeneous equation and the solution for a particular equation and add them back together. Yeah, question? Oh, did I miss that? Yeah, I think I missed a negative up here. Did I? Yep, I missed a negative up here. Sorry about that. Up here. Right, because we have minus t infinity times this here. Yeah, thank you. Okay, so this is our the solution that we need to work with. And again, what we're trying to do is find separately a homogeneous and a particular solution and add them back together. So what does it mean? What does it mean to be a homogeneous solution? Or what is a homogeneous equation in ODE? What does that actually mean? It means that I can take my equation or the solution to that equation, and I can multiply it by anything I want to multiply it, any constant I want to multiply it by, and there remains a solution. This is just a definition of a homogeneous ODE. So in practice, what that means for us here is I need to take that homogeneous piece, set it equal to 0. Okay, the homogeneous piece then can be multiplied by anything. It still remains a solution because it's equal to 0. Okay, so let's move on to that. So let's first, let's solve the homogeneous part first. So don't worry about what's on the right-hand side. We'll get to that. So let's start with the homogeneous piece. That means I'm going to take d squared t h dx squared, minus parameter times h bar over KAC times th, and that has to equal 0. All right, so I'm taking that th part of the equation, saying this has to equal 0. I can multiply that by anything I want. It's still going to be a solution. Okay. All right, so how do I solve this? Well, here's your clue over here. Rather than having to go and solve this equation, we're trying to find an equation for th that satisfies this ODE. Well, I can, instead of trying to do this by hand, just go to these tables. So pretty much any ODE like this for homogeneous solutions, there's going to be a table you can go and find, right? If you're having on the test, you'll be given this table. You don't have to worry about it. But what you really have to do then is just go through and say, okay, which of these solutions looks like the thing in the first column, the linear homogeneous ODE, and you match that up, and then you say, here's my solution. Okay, so it's pretty easy. It's just pattern matching, we'd call it. The only tricky part is to figure out what is what's this sign here, like what's the sign doing. So we already know, okay, I've got kind of two candidates here, this one and this one. This is really the only forms that would fit. Sorry, let me zoom in a little for your benefit. So we have minus m squared t or plus m squared t. All right, let's look over here again. We have to be a little bit careful because, let's say I went through this derivation and it turns out that h bar, for example, is always negative, right? If it's always negative, then the sign on this is actually plus. So let's look at the physical quantities here: parameter, convection coefficient, conductivity, and area. Are any of those ever going to be negative? No, right? So this, in fact, is a negative sign. It's truly a negative. So we go over here, and we're going to have to pick one of these two solutions. Right? Which one do we pick? Actually, mathematically, these are equivalent, right? Exponentials and sinh and cosh, these are hyperbolic sine and hyperbolic cosine. They're mathematically equivalent. In fact, if you look at the definition of cosh and sinh, it's defined in terms of exponentials. Okay, so these are equivalent solutions. Which one would you want to use? Well, it turns out if you have a boundary condition or like a semi-infinite wall, you'd probably want to use exponentials. For pretty much everything else, we're going to use sinh and cosh. Okay, so we're going to go, let's pull off this solution, sinh and cosh. And now we've just gone through this process to say th, the solution for this, th is now c1 cosh of mx plus c2 sinh of mx. Sorry, it's out of the way. And that's the homogeneous solution, or the solution to the homogeneous part of the equation. Okay. What are these? These are unknown constants of integration, basically. So these are the things we're going to have to solve using boundary conditions. Okay. Great. So that's just that. That's this homogeneous part. For the particular solution, we have to do a little bit, be a little bit more creative than just looking at a table. So here's what we ended up with before. Let's see. So this here was our general solution. This is the particular solution that when you group all the particular parts together, we have the TP terms and then anything left over on the right-hand side. That's the particular equation. Okay. So we ended up with this. Now we need to find a solution for TP. We need to find an equation TP that satisfies this ODE. All right. How do you do this? Well, it turns out basically you just have to stare at it for a while. Okay. And this actually, it has a name. It's called the method of undetermined coefficients. The method of undetermined coefficients says, I'm going to look at this equation and I'm going to find a solution for TP that satisfies this. So what you want to do, just in terms of methodology, is look at the right-hand side first. So let's look over here. Right? We have a constant. So what the method of undetermined coefficients says is, take your right-hand side. That's going to be the form of your guess. Okay, you're going to guess a solution TP. The right-hand side is going to be the form of that equation. You're going to have that, and then any derivative of the right-hand side will be the thing you're guessing. Okay, then you have undetermined coefficients in front of those terms, and you have to then solve for them. Okay, so what does that mean in this case? In this case, it means I'm going to say, let's see, TP is equal to some constant, right? The right-hand side is a constant. I just have to find the right solution that matches up the coefficients on this. So we already used C1 and C2. We'll call this C3. So TP is a constant C3. So I'm going to guess TP is that constant, plus I need any derivatives of that right-hand side. What's the derivative of a constant? 0. Okay. So C3 plus 0, right? So this is what I'm going to guess for TP. Then I just go through and I plug in my guess and see how it pans out. Okay, so let's go over here. So we say TP. So we plug that in, right? We have the second derivative. Let's see here, second derivative of a constant, that's 0. So we have 0 plus perimeter times h bar over k AC is equal to my guess, which is C3. Okay, and then on the right-hand side, I have perimeter h bar over k AC T infinity, right? This goes away, this goes away. Sorry, I have minus here, 0 minus, right? Minus. So the minus, all that stuff goes away, and we end up with C3 is equal to T infinity, right? And up here I said TP is equal to C3. So there we are. So now the last step before you guys pack up is to put it all back together. So T was T homogeneous plus T particular, right? So that just means I have my final solution is C1, what was it, C1 sinh of M times X plus C2 cosh of M times X plus T infinity, right? This now becomes my general solution. I have to go through and force boundary conditions, which we'll do next time. Okay. All right, thanks. See you Friday.